Okay, so today we'll say a few more words about EM algorithm and how it might be used for missing data. I want to mention a couple of other models that we won't discuss in this class, because this is more or less the last lecture that I'm giving, but which are good to know about. So the EM algorithm, remember the E stands for expectation. We fill in the missing or latent data that we expect to be there. And the M stands for maximization, using that kind of imputed. It's imputing, but it's not exactly imputing, because, for example, there's no restriction that the data have a form that may be integers if it's count. And then in the maximization step, we're taking this fake data mixed with real data that we filled in, and we're using that data to find an optimal value of the parameters. And it's useful for hierarchical models with hidden variables or latent variables. So that's an example of a situation in which we have missing data, but the missing is kind of by design, right? There's some variable that we think is important, but which we've never observed. And by hierarchical models, I'm talking about hierarchical log linear models, and including in that the graphical models, which are sort of perhaps the most important subclass. And it can also be used to impute missing values in contingency tables, generally. And in some sense, right, this is just the general thing, and then a special case is the special format of being missing. And it's useful for a lot of other things as well. Whenever you have this kind of situation where there's something you don't know, but you have a simpler model that describes what's going on in terms of the unknown, you can go between these. So in some sense it's an algorithm, in some sense it's kind of a meta-algorithm, or something which, a principle from which you can derive other algorithms, just like maximum likelihood. So we're alternating between fixing the parameters and fixing the known data and estimating or finding the expected missing data. And fixing the complete table maximizing the likelihood and define the new parameters. Iterate until convergence. And we talked about at the end of last time that we restart as needed. So we sometimes need to restart the algorithm because we can't expect, the sort of theorems that govern it tell us only that the likelihood will increase with each iteration, with each new theta, but it gives us no guarantee that we'll ever reach the global maximum. Of course, restarting it also doesn't guarantee that we'll ever reach the global maximum, but it gives us a better shot, right? Because it gives us a better chance that we didn't get stuck in an unusual corner, but that corner could be arbitrarily small without further information.
What's like the Newton-Raphson? How does that like not get lost in the?
Oh, it most certainly can. So all these iterative algorithms can get lost in. The difference is that many of the cases where we've applied it so far, they had a unique maximum. So there was a way to prove that there was only one maximum, and so it'll get there. The difference is when we start to add hidden data or latent variables, it will almost never be true that it has a unique maximum. Right? So, that's not what I want to say. It will almost never be true that it has a unique critical point. Right? So when we add this stuff in, there's going to be more critical points in general, and so that's why this stuff becomes necessary. The hill climbing algorithms only ever climb hills. It's just that the models that we've been looking at have a simpler topography. So ways to choose this. So we said we could choose this randomly, the starting value. We could choose it to induce a uniform distribution. In other words, make it all ones or something, all zeros depending on the scale. A sensible thing to do might be to use a smaller complete data set. So, you kind of want to have a prior on what this thing should be. So if you had a big missing data set, data with some missing, and you had some examples that were complete, or you're doing a complete case analysis, or you had a more carefully done, smaller experiment, that would be a great thing to use to get a sensible starting values for your parameters. Or you might even just use a simpler model. For example, suppose you're trying to fit a model like this, where I have a latent variable and I have visible variables. I might just start with at least fitting the independence model, and then picking something else for the other parameters. Right? So I have some simplified model for which I do have all the data, and use that as a hint to start the process. And sometimes this kind of, for very complex models, like we'll talk about at the end, that have this structure, like neural network models, for example, that you hear about nowadays being used to do all sorts of complicated learning tasks. For those, this problem of where to start is very important because the optimization space is enormous. There's tons of local maxima. And so a lot of effort was spent. Basically, the thing that caused the breakthrough ultimately was a procedure for finding a nice starting point for an iterative optimization. Okay. So one thing we can do to apply, so I'm going to sort of say what an obvious thing to do, and then we'll talk a little bit about when that might make sense, sort of backwards. But so the obvious thing to do to apply EM to missing data in the sense of rows, that is, we have something like, we have an observation 1, observation 2, observation 3, observation 4, and so on. And we have, the x1, y1, z1, w1, and this one, the x is missing. In this one, the y is missing, and so on. Different. Maybe the first two are missing, and then z, 4, w4. So there's different missingness patterns. And usually in this, we want to do something like we can think about maybe x as being the whole thing, and this is x restricted to the missings, and this is x observed. And what's special about the latent variable case is that this partition of the sort of true data vector into missing and observed is always the same. And in this case, we're just allowing that to also be a variable that varies by row. So the obvious thing to do would be pick some starting parameters. By some method. Those methods. Like using complete case analysis. Impute the missing points. So using the parameters, I could just go and fill in for each of these values some value. Okay, it's not crazy to do. We could take the most likely value. Of course, we talked about some of the biases that will introduce. So we could look at the most likely. or we could use some randomized version. And if we're doing an iterative randomized algorithm where we're imputing data and we're adding some randomness to it each time, then we're really doing a kind of a Monte Carlo analysis. And there's more to say about that, which again I won't get into. And then re-estimate the parameters. And iterate until convergence. So that's basically taking the same approach we took to the case where where this division between missing and observed was always the same, and just sort of applying it. So now I want to go back to our different types of missing and say something about when this sort of procedure makes sense. So recall that we called it missing completely at random, and where m is some sort of either scalar, like binary, or maybe it's a vector of missingness, like it could be a mask, right? Like a realization of m might be that, which says this place and this place are missing. So this vector that controls, random variable that controls the missingness, the m car is if the probability distribution of m, given the rest of the data and the parameters, depends only on the parameters, i.e. the random vector corresponding to the missing data and the random vector corresponding to the underlying data. They're independent once I know the parameters. And this includes missing by design. So for example, it's too expensive to measure some of the parameters, so I randomly choose a subsample of my whole sample and figure out what the data that's expensive to get. Or maybe the first 100 people, I make them answer every question on my survey by standing over their shoulder, and then the rest of them I let them do whatever. Right? So I have some design that causes the missingness. And another way of thinking about that is this is also missing by design, this latent variable where I never know. By design, I never ask that question. I never know what that variable is. And so that's kind of weird because we're saying that this random variable missingness, even though it's completely by design, we're giving it the name missing completely at random. Of course, it's not random. We're saying it's deterministic. But it still can satisfy this kind of independence relationship because, well, it certainly doesn't depend on x. It doesn't depend on anything. It's part of our design. That's why. Right? It's like saying a constant is independent of something else. Because we're treating it as constant. Even though the word missing completely at random doesn't necessarily mean there was actually any randomness in the choice of which variables, which things are missing. It's a little confusing. And then we had missing at random if the distribution sorry, I keep writing y of the missingness conditioned on x, the rest of the data and the parameters is the missingness depends only on the observed things, and the parameters in terms of conditional independence, we're saying that the missing is independent of the missing part of the vector given the observed part of the vector, and of course the value of the parameters. So we're saying what the missing at random says that there can be dependence, but the dependence all factors through the observed part. So once you know the observed part, there's no dependence left between the things that I missed, the data that's just gone, and whether they're missing. I've completely explained away, for example, the salary thing. Right? People don't want to talk about their earnings. If I have enough variables here that I can predict whether or not they'll answer, I don't have to worry about the fact that there's a relationship between earnings and whether or not they report them, because they become conditionally independent. And then in this language, missing completely at random is the stronger assumption. And otherwise, we might say it's not missing at random. And so, as I'll emphasize again today, the best methods model missingness. So in other words, rather than tacking on some additional assumptions or thinking of, or pretending that missingness was impossible, even though we observed it with positive probability, they push this variable m somehow into the model and model it explicitly. In some sense, that's the only time you can really be said to be doing something statistical. Unfortunately, the bad news about that is it means that you need, if you have data where everything observed was a perfectly clean, generalized linear model, hierarchical model that we learned about in this class, and then when you add missing data, it's no longer that. It just means, well, okay, we have to use a more complex model. Okay, so supposing that the data are missing at random, let's think about how EM works. So we've succeeded in at least this conditional independence. So that says in some sense that we can ignore the missing data. Ignore it in the sense that it's safe to marginalize over it. Right, we're sort of putting in our graph, we have the missing data, and we have the rest of the data, and this is x observed, and this is x missing, and it's safe to sort of sum out this to make inference about that part, just like it was when we saw conditional independence before. So our data is the missing part, say union the observed part, and the difference here now is that this combination can be different for every row. So we have a log likelihood for the complete data. And then we have a marginal or incomplete log likelihood where we have to sum over or integrate over the things we didn't see. We don't know what happened, but we have some idea of a probability distribution at what might have happened. So this is the likelihood of the observed data with respect to the parameter. That's just observed parameter. And this quantity here is really an integral of a density that involves both the missing and the observed data, and the parameters where we're integrating out the missing data or summing out the missing data, or summing over it. So, put it this way, sort of summing over all of the missing entries in a screen that I just erased, it's the same kind of situation as this type of diagram where I have a hidden variable that I don't observe, and I have observed variables, and I have to compute a likelihood function based only on the parameters and the observed data. Right? And I do that, or one step in doing that, or in constructing that likelihood function, is that I have to sum over the hidden states. Similarly, I'm summing over hidden states. They're just not as well structured. So we said that in the E step of the EM algorithm, what are we doing? We're imputing the missing data. So in the E step of the EM algorithm, for contingency tables, we're filling in cells. So the most general thing we could sort of do, or the most specific, depending on how you look at it, general or specific, is we could fill in actual observations. We could complete our observations to be the most likely observations. We could fill in the cells. Of course, these two things are still too much work, right, in the EM algorithm. So we could fill in all the observations, but we don't really care about the individual observations in finding out theta. Right? Our next step is going to be the maximization step. So we want to pick a new parameter vector based on this information, right? So from this, we construct a likelihood. Right? We can start with the observations and construct a likelihood. We can summarize the observations into cells and construct a likelihood. Right? So this is way too much work. This is still too much work, right? Because all I really need is what? For a log linear model. I don't need all the observations. I just need the cell values. But I don't even need the cell values. What do I actually need?
No, counts.
Yeah, the counts, right? I need this matrix A times the cell values. Right? So you can think about the cell values as being a vector. I take this matrix, and this summarizes them. It figures out which statistics do I actually care about. Which statistics go into my likelihood function. So when you think about it that way, what's really the job of the E step? It's not to fill in the data or fill in the cells. It's to find the function that we're maximizing. Right? All we care about is that this step, the E step, produces a function which is maximized if and only if the likelihood function is maximized. It doesn't even have to be the likelihood function. It just has to be something that when I maximize this, whatever the function that it outputs, it's the same as maximizing the likelihood in this step. So filling in the observations, filling in the cells, computing the sufficient statistics are all just steps along the way of making a likelihood function. Right, so creates a likelihood, but or something equivalent. So something which is maximized if and only if the likelihood function is maximized. So that's nice, because that tells us that if we're sufficiently clever, we don't have to guess the observation values. We don't even have to guess the cell values. We don't even have to guess the sufficient statistic. All we have to do is come up with a function that does a good job. Right? So sometimes it's easier to think about this function, this likelihood function, as not being literally a likelihood function, but being more like a likelihood ratio. That is, I have some old parameter value, let's call it theta old. I have a new parameter value, theta new. And all I need to do is take a function that eats these two things, and let's call it Q. And this changes, so I want to argmax theta new. I move around theta new, and I want this function to be, depending on how I look at it, maximized or minimized. Let's say maximized. How maximized is how much better theta new is than theta old. Right? That would be sort of as efficient. So instead of saying, okay, factor out the observations into the cells, factor the cells through the sufficient statistic to get a likelihood function. But the likelihood function you could think of as having kind of a level and a change. It has some level, and then I have a vector of how my theta has moved. And if you think about like what's the derivative of that with respect to that vector, that's the only information we really need, right? We just need to know in what direction does the likelihood function improve. How do I move my theta around to get it to improve? So that's more of a likelihood ratio. So let's say this Q theta new given theta old is like expectation under theta old. And this is sort of taking the likelihood. Actually, I'll write it up here because it's going to be too small. So that's equal to, I'm setting it equal to the expectation under the old theta of the log of the density x missing, little x observed, and theta nu, divided by the density of x missing, little x observed, theta old, given that x observed equals little x observed. So what am I saying here? I'm saying that this is just another way of saying I'm marginalized, right? The goal is to marginalize out to sum over the missing values. So what I'm saying in terms of summing over the values, I want to take the expectation, which is just a type of integral, summing over all the values times their probability. The density of the missing and the observed I can treat as fixed because the observed data I know what it is. The only thing I have to treat as a random variable with respect to this expectation is the missing data. So I've capitalized the missing data because I'm treating that as a random variable. I've lowercase the observed data because that's something that is fixed once I make my observations. And then it depends either on the new or the old parameter. And so my job to update the parameter vector is just to maximize this function, this likelihood ratio, maximize my improvement of theta nu versus theta old. Okay. Log f of x missing x observed, theta f of x missing x observed, theta old, nu f of x given x observed, theta old dx. I just want to make it into an integral that I can do in theory. So then what we're saying is that we've reduced the e step by multiple factorizations to just having the job of computing this expectation. That's why it's an e step. Right? This is it's computing an expectation. And then the function that this creates, this q function, which is now a function of one variable, theta nu, it's the job of the m step to just maximize this function with respect to m. Okay. Yeah.
I was wondering, so we're assuming that the expectation operator and the logarithm operator, they are kind of changeable. So I was wondering whether here we're going to make some function for the f function.
Well, they're not exchangeable, though.
It's not exchangeable.
Yeah. There's some inequalities that you can get, right? You have a convex function and an integral. So you can use Jensen's inequality, and that's the strategy. So you can think about, if you do that, you push the integral through, you can think about that as creating a lower bound on your expectation. You can try to maximize the lower bound instead. And that's often a good idea because it's often more tractable. So people do that, but that's not what I'm going to do right now. Okay. Okay, so again, because all we did was change notation. This theorem that I talked about last time, which is that as long as I do this maximization, the likelihood will keep increasing, still holds, because I'm still conceptually doing that. I've just changed. What's the point? What's the advantage? In many situations, right, we used to have just a raw probability distribution, and now we have a ratio. So if there are any constants, for example, like big, nasty, intractable constants, they're just going to cancel, or almost cancel, if these two aren't too far apart. And in general, that when you have a ratio like this, it often simplifies things a lot. So a lot of terms in this are going to cancel with a lot of terms in that. So this is often a lot easier to compute than the sort of straightforward version. And that's one of the reasons people do that. Basically because of cancellation. Okay, so I'm not going to get any further into the details of how this works, but I just want to give kind of a passing shot about missing data. Or a principle. So I would say that bottom line on missing data is that there is no such thing. Does that make sense? What do I mean by that?
We're putting something there.
Huh?
We're putting something in.
No, not quite.
Once all our data is collected, that's actually, it's still complete, just the fact there's a zero in that cell, it's just down to the.
Yeah, right. That's the idea. Is that there's no such thing as missing data. Just misspecified models. Right? Missing data is a symptom of trying to apply a simpler model than the situation warrants. Right? It's if you take a model which assumes that it's impossible for someone to not answer a question, they in fact don't answer the question. Therefore, your model was wrong. Your model was misspecified. And so sometimes it's okay to use a misspecified model, right? Like all models are wrong, some models are useful. You have to justify why it's still okay, or use a better specified model, a model that includes the possibility that incomplete data can happen, because that's the reality that you're dealing with, right? That's like the physical reality. So although you can get away sometimes with a model which ignores the possibility of missingness, you're essentially using a misspecified model for a more complex data set, and the right thing to do would be to expand your model in order to incorporate the possibility that it's missing. Okay. So I have a few more minutes left, and what I want to use that time for is to discuss some of the other things that can happen now that we have the idea of latent variables. So kind of further uses of latent variables and missing variables. Right? Now that our model is not misspecified anymore, what are the new possibilities? And one of the things this is related to is how do we generalize conditional independence? Conditional independence is a very nice relationship. It has a lot of good properties, and it describes the model in kind of a dual way, where we can say what axioms does the model satisfy, how does the model factor? And is it possible to generalize that kind of idea to situations where we have latent variables? So sort of a motivation, I mean, these graphical models, so I use this example. These graphical models where some of the variables are visible and some of the variables are hidden are really kind of taking the world by storm, largely under this name of neural networks, right? If you read about, I don't know, these AlphaGo and all this other kind of crazy stuff, right? So what is that? It's a neural network, which if you look closely enough, at least in the way it began, there's lots of tweaks on top of it, but it's just a huge graphical model, like millions of variables with lots of hidden variables. Right? And it has some kind of complex hierarchical structure, and it's fitting this model by using some kind of iterative algorithm. It's not so different from the EM algorithm. Okay? And, they've evolved in the sense that they started out as models that were more or less probabilistic, and then you could attach a probabilistic interpretation to them. As they evolved, it doesn't necessarily have that interpretation anymore. So for example, there's kind of link functions in here, right? If I derive the conditional probability of this being on, given that that's on, it has a certain form that's forced by the log linear structure. They might, which is like a sigmoid function, like e over 1 plus e to the x, 1 plus e to the x kind of stuff that we had to do in logistic regression. So they might take this function and change it, like, oh, let's use this function because it's easier. Right? So, but it sort of conceptually still has origins in probability. This one, by the way, is called a naive Bayes model. And there's examples of using it for things like classification. It's basically a logistic regression. You're trying to make a decision about this hidden variable is an email message spam or not, and you look at a bunch of visible variables. And you train it on maybe a complete data set that includes that. Some other examples of this type of model that are a little simpler are things which are used in vision and spatial statistics. There's something called a Markov random field, which is basically a graphical model that lives on a lattice, like a square lattice. So in this picture, all of these variables are observed. There's no hidden variables. It might look like that. And so this is just a straight hierarchical model, like the ones that we've learned about, a log linear model. We have parameters associated to edges and to nodes. And these are used for, you can imagine being used for vision, like these are on or off, like a pixel is on or off, or a pixel has a certain intensity, and you can use it to segment images, for example, decide what's foreground, what's background. The first papers about this were actually purely sort of spatial statistics. So there's this paper by Misspecified, that's one of the important kind of original papers. And what he was doing was modeling spotted wilt, which is a thing that happens to tomato plants. So he was looking at fields of tomato plants and talking about how is an individual tomato plant being sick relate to the ones around it being sick. And a sort of similar thing where you get sort of patches of sickness, right? There's something called a conditional random field, which is one of something like this that has also hidden models or hidden variables. In a conditional random field, it's like a Markov random field, except that I make all of these things in the grid hidden, and I attach a visible variable to each one. So all I observe is a visible variable, and I believe that there's some hidden spatial structure underneath. And I have to estimate that spatial structure based just on this, what I've observed here. A simpler version of that is something called a hidden Markov model, where I have transitions between hidden states. Like a good example for a hidden Markov model is something like the economy. There's a hidden state, which is the economy in recession or not? And then there's some observable thing like macroeconomic statistics, employment percentage or whatever, with stock market going up or down, and you have to make the inference, was this caused by this hidden variable being 0 for recession or 1 for not recession? And so people use this kind of model to make smoothing decisions, right? So like this sequence might be very variable, and then you can create a hidden sequence which simplifies this, like on, off, right? Lots of variations on that. So I mentioned these neural networks. So this one of the most popular now are these deep learning models, and you know enough that I can tell you the basic idea of a deep learning model. So you start with this logistic regression or naive Bayes thing. So you have a hidden variable, and then you have some observed variables, and then what you do is you start adding more hidden variables. So this is just a graphical model. It's a big, complicated looking graphical model. It's just a graphical model which is complete bipartite. There's some number of hidden variables, there's some number of visible variables. And this thing is called a restricted Boltzmann machine. And what's a deep learning model is just a stack of these things. So I have a restricted Boltzmann machine. On top of it, I put another restricted Boltzmann machine. On top of that, I put another restricted Boltzmann machine, like that. And then the idea that people had that led to the first breakthrough in using these was to train them layer-wise. It was how do they had an iterative algorithm for improving the likelihood of the whole thing. But it was such a complex model that if they just started at a random place or they started at a uniform place, they would never get to a good answer. It would find some local maxima that wasn't good enough. So what they did was they figured out that if they train it layer-wise, so you start with the very bottom one and you try to estimate that one until you're done, and then you feed inputs into this, estimate the most likely hidden nodes, and use that as input to the next layer, try to fit the parameters on that layer to maximize likelihood, and so on, and then use that whole sequence as the starting point for a further iterative algorithm. Then they were able to get to a good maximum, and that sort of happened around 2006 and led to the explosion in neural networks that led to things like AlphaGo beating people. So this thing is called a deep, well, literally a deep restricted Boltzmann machine, or a deep belief network. Maybe change these arrows to all pointing down, which specifies a different model because undirected and directed graphical models are not the same. So as these models get more complex, you might wonder, does any of the principles that we talked about in this class still apply? And the answer is a little bit yes and a little bit no. So for example, you can ask things like, are there conditional independence like rules that describe the dependence structure? Of, say, graphical models with hidden variables, with latent variables. Variables which are never observed by design. And I could ask questions like, how do we measure goodness of fit for these more complex models? For example, can you tell me what the degrees of freedom are? So we certainly know questions like, say for this model, we know how many parameters there are. That's how when I put them in. But that's not equal to the degrees of freedom anymore because we're marginalizing so much out, right? So one of these models, we're summing over lots of hidden states, right? In the extreme, right, I could have some model where, I don't know, this is my model. I have a very complex graphical model, and I say this one is observed and everything else is hidden, right? There's tons of parameters, but most of the parameters don't matter. So there has to be some smaller effective degrees of freedom. Right. So in order to understand something like that, we'd have to figure out what the degrees of freedom are. So the kind of situation here is that the answers to these sorts of questions, how many degrees of freedom does a deep belief network have? Or are there conditional independence rules that, like rules that somehow describe the structure with latent variables? The answer to both questions is, in principle, we can answer those questions, but in practice, they're usually too difficult. And so it's really hard to answer them, or it takes a lot of work because of the complexity of the models, essentially. There's a lot of, they're computationally difficult and practically difficult. Let me say a little bit about how you would go about answering this first question. So without hidden variables, the hierarchical models with categorical variables that we've talked about in this class can be described provided that all the probabilities are positive. This is that Hammersley-Clifford theorem. by conditional independence statements. Right? There's some amount of conditional independence statements that pretty accurately describe what probability distributions could come from that. In other words, if the probability distribution satisfies all these conditional independence statements, I can say it comes from the model. If it doesn't, then I can say it doesn't. There's a little bit of detail, edge cases to that, but it's approximately true. Another way of saying is I can take these conditional independence statements like A independent of B given C and turn them into equations. Right? Whenever I have an independence relationship, like A and B are independent, says that the probability of AB is equal to the product of the probabilities of A and the probability of B. Right? So if I wanted to turn a conditional independence statement into something, I could just, this is A is independent of B. I could just say probability of A, B, C equals probability of, where C is some fixed value, AC, let me go this way. Let me go this way. First, let me rewrite this one now to make it clear. PA, PB, what do I want to say? Think about this for a second. Okay, so the point, what I'm trying to say is that this, so you turn this into equations. There are equations that have to hold among these PABs, like PAB, PA prime, PB prime equals PA prime B, PAB prime. So if I were just saying A is independent of B, it would be the same as saying this or the same as saying that. Right? It says that this is another way of saying that the 2x2 table, the odds ratio is 0. Or the odds ratio is 1, or the log odds ratio is 0. Right? We're talking about a 2x2 table. We're saying that the odds ratio goes away. Similarly, you can take this type of statements and turn them into equations. And for all the hierarchical models that we've talked about, they have this amazing feature that the conditional independence statements or the model itself can be described by binomial equations like this. That is, I can write down a bunch of equations, some probabilities multiplied on one side equals some probability multiplied on the other side, such that if all of those equations are satisfied, then modulo edge cases, that probability distribution belongs to that hierarchical model. What happens when we go to things that have latent variables is that you can still describe them in terms of equations, but the equations get much more complicated. They're no longer a bunch of things multiplied equals a bunch of things multiplied. They become arbitrary polynomials. And so, for example, if I do something like this, and I say I have two hidden states, and I have a bunch of visible variables, I can write a table that has all of these variables in a big matrix. And no matter how I do that, it turns out that in this case, the 3x3 minors of that matrix, the determinants of any 3x3 submatrix will be 0. Basically, we're saying that this thing kind of has, any matrix I can form from this has rank only 2. It's like a generalization of independence, right? While that's true, only in small cases like this number being 2 is that enough to describe the space. So as we go increase the number of states here and the number of states here, in general, we don't even know what those equations are. Still open question what those equations are. But we can ask the question at least. So then, the second, in answer to this second question, I'm not even going to touch goodness of fit, but let me talk about degrees of freedom. So, geometrically, I kept drawing these pictures like this, right? Where I have a model, which we usually thought of as a hierarchical model. It sits in some side of, so this is a small model. It sits in some larger model, right? Maybe it's a more complicated, this is independence sitting inside of dependence, or something more complicated, right? And we computed the degrees of freedom by taking the degrees of freedom of the larger model and subtracting from it the degrees of freedom of the smaller model. What this picture, I hope, suggests is that I can replace the idea of degrees of freedom with the geometric idea of dimension. What we're saying is that we take the dimension of the larger model and we subtract the dimension of the smaller model to get the degrees of freedom of the test. Okay? So the answer to the question, what are the degrees of freedom or the effective degrees of freedom to such a thing, is the same as the question of you specify a model using some kind of graphical notation and you ask what is the dimension of that model. So this is also a very hard problem. So for example, with some co-authors, I've written 3 papers about just this one, restricted Boltzmann machine. What is the dimension of the restricted Boltzmann machine? How many degrees of freedom it has? And that's something that, it took about 5 years to go from here's an upper and lower bound on the dimension to here's a better one to finally now we know the answer of what the dimension is. But that stuff takes a lot of gymnastics, though it's not impossible. Okay, so that's it for today. Actually, I'm done, and that's.